Okay, welcome to week 5 of Machine Learning Foundations. We'll be continuing the discussion of linear algebra all through this week and one more week after this. The goal of this week's lectures is to finally get to the most important theorem in linear algebra, the spectral theorem. We'll cover this in a more general form, not necessarily for real vector spaces, but in the context of a complex vector space. The important class of matrices that generalizes real symmetric matrices is called Hermitian matrices. So we'll prove the spectral theorem in the context of a Hermitian matrix. The main result, in very simple terms, is that every Hermitian matrix is orthogonally diagonalizable. As a gentle start in this lecture, we'll look at complex vectors and complex matrices and try to understand how we can define the inner product between two complex vectors in a natural way. We'll also define what it means to take the conjugate transpose of a complex matrix and use that notion to define a Hermitian matrix. We'll denote the space of complex vectors as Cn. This is the complex counterpart of the usual Euclidean space, n-dimensional Euclidean space, Rn. So when I say x1 up to xn belongs to Cn, I mean each xi is a complex number for I equals 1 to n. Now, this is something you may already know, how to add complex numbers. If I have a plus ib plus c plus id, I add the real and imaginary part separately. Multiplication works out to a c minus bd plus I times the quantity bc plus a d. I hope you're all familiar with this already, so I won't spend too much time on it. The important thing to understand next is the complex conjugate. The complex conjugate of a complex number plus ib is a minus ib. One way to understand this is through polar coordinates. You can represent a plus ib as r times e raised to the power I theta, where this is the real axis and this is the imaginary axis. The conjugate is then a minus ib, and it can be represented as r times e raised to the power negative I theta, where r squared is just the squared length of this vector. Now, you can take linear combinations as before, with a slight tweak. If I write c1 times x1 plus, and so on up to ck times xk equals 0, taking k vectors, the difference from before is that these scalars, the c values, can now be complex numbers, and the vectors belong to Cn. The next bit of background to cover is the inner product, and the concept of the length of a vector in the complex case. Recall that in Euclidean space, the dot product was your inner product, and it was used to define the length of a vector. We can't use that same definition in the complex case because it doesn't match our intuition. For example, using that same formula, what would be the length of the vector 1i? It would just be 1 squared plus I squared, which comes out to 0. So for a complex vector space, we define the inner product a little differently, using what's called the conjugate. If I want the dot product of x and y, it's x bar transpose times y, meaning I take the conjugate of the first vector and multiply it with the second. An important thing to note here is that x bar transpose times y is definitely not equal to y bar transpose times x in general. If you take real numbers, real x and y, this relation would hold, but that's only true for real numbers. You need complex numbers to see the difference. For example, take x as 2 minus I, 1 plus I, and check that x bar transpose times y is not equal to y bar transpose times x. Now, how do we define the length of a complex vector? For x and Cn, we define the length as the square root of x bar transpose times x. With this, what would the length of the vector 1i be? It would not be 0 once you take the conjugate into account. You can check that it works out to the square root of 2, not a zero-length vector, which matches our intuition. So 1i is not a zero-length vector, and our definition only gives a zero-length result if the vector itself is the zero vector, otherwise we won't get a zero length. Now let's check a couple of properties. The first can be verified directly from the definition. If you take x dot y, it equals the conjugate of y dot x. And if you take x dot a constant times y, this equals that constant times x dot y, simply because you're taking the conjugate of the first component in the inner product, but the same isn't true if the constant multiplies the first vector instead. In that case, the constant comes out as its conjugate. You can check this using the definition of the dot product, that is, x dot y equals x bar transpose times y, or the sum of I of x bar I times yi. Given this, we define what's called the conjugate transpose. Everyone knows the regular transpose, here you add the conjugate as well. So a star is the matrix that is the conjugate transpose of it, defined as taking the conjugate and then the transpose. You can do this in either order and you'll get the same result. As an example, suppose there's the matrix with entries 1 plus I, 3 minus 2i, 2 minus 4i, and I. Then a bar, the conjugate, would have entries 1 minus I, 3 plus 2i, 2 plus 4i, and 1 minus I. And the star equal to a bar transpose, we would get the same result whether we transpose first and then take the conjugate, or take the conjugate first and then transpose. Either order gives the same answer. An important remark: for a real matrix, a star is nothing but a transpose, because for a real number, it's its own conjugate. Now, some claims which again you can check yourself. These are just the equivalents of properties we already know for the regular transpose. If you take a star and then take the star again, you recover, and the star of a B equals B star times the star. In the real case, the equivalent statements are that the transpose of A equals A, and the transpose of a B equals B transpose times the transpose. Just to reiterate the inner product, so we have it defined in one place, x dot y equals x bar transpose times y. That's x1 bar times y1 and so on up to xn bar times yn. This can be written as the vector x1 bar through xn bar dotted with y1 through yn. But this is the same as x star times y. So x dot y equals x star times y. The last definition before we close this lecture is what's called a Hermitian matrix. A matrix is Hermitian, which is the complex equivalent of a symmetric matrix if a star equals A. Hermitian matrices are the equivalent of symmetric matrices in a complex vector space. For a real symmetric matrix, you have a transpose equals A, and for a Hermitian matrix, if you take the conjugate transpose, it's the same as the original matrix. So a quick recap before I end this lecture. What did we cover? At a high level, we understood how to define the inner product between two complex vectors, and this involved to change. Specifically, we had to apply a conjugate operation in addition to the usual transpose. The second thing we looked at was the conjugate transpose, a notion that, when applied to matrices, lets us define a Hermitian matrix, one where the matrix and its conjugate transpose coincide. This is a very important subclass of complex matrices, which we'll be focusing on because these are the matrices that turn out to be orthogonally diagonalizable, as will become clear as we move through the lectures this week.
Okay, welcome to week 5 of Machine Learning Foundations. We'll be continuing the discussion of linear algebra all through this week and one more week after this. The goal of this week's lectures is to finally get to the most important theorem in linear algebra, the spectral theorem. We'll cover this in a more general form, not necessarily for real vector spaces, but in the context of a complex vector space. The important class of matrices that generalizes real symmetric matrices is called Hermitian matrices. So we'll prove the spectral theorem in the context of a Hermitian matrix. The main result, in very simple terms, says that every Hermitian matrix is orthogonally diagonalizable. As a gentle start, in this lecture we'll look at complex vectors and complex matrices and try to understand how we can define the inner product between two complex vectors in a natural way. We'll also define what it means to take the conjugate transpose of a complex matrix and use that notion to define a Hermitian matrix. We'll denote the space of complex vectors as Cn. This is the complex counterpart of the usual Euclidean space in dimensional Euclidean space Rn. So when I say x1 up to xn belongs to Cn, I mean each xi is a complex number for I equals 1 to n. Now this is something you may already know, how to add complex numbers. If I have a plus ib plus c plus id, I add the real and imaginary parts separately. Multiplication works out to a c minus bd plus I times the quantity bc plus a d. I hope you're all familiar with this already, so I won't spend too much time on it. The important thing to understand next is the complex conjugate. The complex conjugate of a complex number plus ib is a minus ib. One way to understand this is through polar coordinates. You can represent a plus ib as r times e raised to the power I theta, where this is the real axis and this is the imaginary axis. The conjugate is then a minus ib, and it can be represented as r times e raised to the power negative I theta, where r squared is just the squared length of this vector. Now, you can take linear combinations as before with a slight tweak. If I write c1 times x1 plus, and so on up to ck times xk equals 0 taking k vectors, the difference from before is that these scalars, the c values, can now be complex numbers and the vectors belong to Cn. The next bit of background to cover is the inner product and the concept of the length of a vector in the complex case. Recall that in Euclidean space, the dot product was your inner product and it was used to define the length of a vector. We can't use that same definition in the complex case because it doesn't match our intuition. For example, using that same formula, what would be the length of the vector 1i? It would just be 1 squared plus I squared, which comes out to 0. So for a complex vector space, we define the inner product a little differently, using what's called the conjugate. If I want the dot product of x and y, it's x bar transpose times y, meaning I take the conjugate of the first vector and multiply it with the second. An important thing to note here is that x bar transpose times y is definitely not equal to y bar transpose times x in general. If you take real numbers, real x and y, this relation would hold, but that's only true for real numbers. You need complex numbers to see the difference. For example, take x as 2 minus I, 1 plus I, and check that x bar transpose times y is not equal to y bar transpose times x. Now, how do we define the length of a complex vector? For x and Cn, we define the length as the square root of x bar transpose times x. With this, what would the length of the vector 1i be? It would not be 0 once you take the conjugate into account. You can check that it works out to the square root of 2, not a zero-length vector, which matches our intuition. So 1i is not a zero-length vector, and our definition only gives a zero-length result if the vector itself is the zero vector, otherwise we won't get a zero length. Now let's check a couple of properties. The first can be verified directly from the definition. If you take x dot y, it equals the conjugate of y dot x. And if you take x dot a constant times y, this equals that constant times x dot y, simply because you're taking the conjugate of the first component in the inner product, but the same isn't true if the constant multiplies the first vector instead. In that case the constant comes out as its conjugate. You can check this using the definition of the dot product, that is, x dot y equals x bar transpose times y, or the sum of I of x bar I times yi. Given this, we define what's called the conjugate transpose. Everyone knows the regular transpose, here you add the conjugate as well. So a star is the matrix that is the conjugate transpose of A, defined as taking the conjugate and then the transpose. You can do this in either order and you'll get the same result. As an example, suppose is the matrix with entries 1 plus I, 3 minus 2I, 2 minus 4I, and I. Then a bar, the conjugate, would have entries 1 minus I, 3 plus 2I, 2 plus 4I, and 1 minus I. And a star equal to a bar transpose, we would get the same result whether we transpose first and then take the conjugate, or take the conjugate first and then transpose. Either order gives the same answer. An important remark: for a real matrix, a star is nothing but a transpose, because for a real number, it's its own conjugate. Now, some claims which again you can check yourself. These are just the equivalents of properties we already know for the regular transpose. If you take a star and then take a star again, you recover. And the star of a B equals B star times a star. In the real case, the equivalent statements are that the transpose of A equals A, and the transpose of A B equals B transpose times A transpose. Just to reiterate the inner product, so we have it defined in one place, x dot y equals x bar transpose times y. That's x1 bar times y1 and so on up to xn bar times yn. This can be written as the vector x1 bar through xn bar dotted with y1 through yn. But this is the same as x star times y. So x dot y equals x star times y. The last definition before we close this lecture is what's called a Hermitian matrix. A matrix is Hermitian, which is the complex equivalent of a symmetric matrix if a star equals A. Hermitian matrices are the equivalent of symmetric matrices in a complex vector space. For a real symmetric matrix, you have a transpose equals A, and for a Hermitian matrix, if you take the conjugate transpose, it's the same as the original matrix. So a quick recap before I end this lecture. What did we cover? At a high level, we understood how to define the inner product between two complex vectors, and this involved a change. Specifically, we had to apply a conjugate operation in addition to the usual transpose. The second thing we looked at was the conjugate transpose, a notion that, when applied to matrices, lets us define a Hermitian matrix, one where the matrix and its conjugate transpose coincide. This is a very important subclass of complex matrices which we'll be focusing on because these are the matrices that turn out to be orthogonally diagonalizable, as will become clear as we move through the lectures this week.
Welcome to Lecture 3 of Machine Learning Foundations. This is week 5, and in this lecture we will introduce the concept of a unitary matrix. These matrices are very important in the context of diagonalizing a Hermitian matrix. You could see unitary matrices as the natural counterpart of what we have seen before, the so-called orthogonal matrices in the context of a real vector space. Now we will define what a unitary matrix is and understand some important properties concerning the eigenvalues and eigenvectors of a unitary matrix in this lecture. But before that, we have to look at this important class of matrices called unitary matrices. These are the equivalent of orthogonal matrices that we have seen before. So, the definition of matrix is unitary if it is a square matrix and has orthonormal columns. Now, if you go back to the real case, our matrix satisfying something like this, we call it an orthogonal matrix. It is equivalent to saying Q is orthogonal, which is like saying that if I take any two columns of Q and take their dot product, then it is 0, and the length of each column is 1. This is equivalent to saying that if Q has columns Q1 through Qn, then Qi transpose Qj equals 0 for all I not equal to j, and the length of each column is 1 for all I equal to 1 through n. So that is orthogonality. Now, the complex counterpart of this, in the complex case, is a unitary matrix. Let's just denote it by U. Instead of just the transpose, you take the conjugate transpose, and you still recover the identity. So U star U equals identity implies U is unitary. Just as Q transpose Q equals identity means Q inverse equals Q transpose, similarly U inverse equals U star. So that is a unitary matrix. These are just the complex counterparts or generalization of the orthogonal matrix that we have seen before.
Let us look at an example of a unitary matrix. Do not confuse unitary matrices with Hermitian matrices. These are two different concepts. As homework, I will leave this check that U is unitary. For another example, if you want, take U equal to the matrix with entries cosine t, sine t, sine t, and negative cosine t. Again, check the same thing. Check if this matrix is also unitary. Now, as in the case of diagonalization, unitary matrices are required for it, so let us look at some properties of unitary matrices. The first property, we will call this length unchanged. That is, in all of this, let U be a unitary matrix, meaning U star U equals identity. Take any vector, then if I apply U to it, its length is unchanged. You can show this. So proof, if I take any two vectors, ux dot uy, this is the same as the conjugate transpose of the first one times the second one. Ux star is x star u star, so we get x star u star ui, but u star u is identity. So this is x star y, which equals x dot y. This implies that if I set y equal to x, the length squared of ux equals ux dot ux equals x dot x equals the magnitude of x squared. That is the end of the proof. So a unitary matrix does not change the length of any vector it acts upon. The second property is the eigenvalues of a unitary matrix U have absolute value 1. That is, if lambda is an eigenvalue of U, we are not saying the eigenvalue is real, please note. We are saying that its absolute value is 1, but it is not necessarily real. So lambda is not required to be real, and the proof goes as follows. We have ux equals lambda x, just to emphasize x is not equal to 0. Also, the norm of ux equals the norm of x. This implies that the norm of lambda x equals the norm of x, which equals the absolute value of lambda times the norm of x equals the norm of x. This just implies that the absolute value of lambda equals 1, since the norm of x is not equal to 0. Now, if you want another one-line proof, using the same idea, you take ux dot ux, this is the same as lambda x dot lambda x. Now, this equals lambda times the conjugate of the second lambda, which is lambda bar times x dot x. This is equal to x dot x, since the norm of ux equals the norm of x. This implies lambda times lambda bar equals 1, or the magnitude of lambda equals 1. That is the end of another short proof. Now, these two properties are a little different from what we had for Hermitian matrices. Again, a unitary matrix does not change the length of a vector, and its eigenvalues have absolute value 1. But a property that it shares with Hermitian matrices is this eigenvectors corresponding to different eigenvalues of a unitary matrix are orthogonal. We can show this from first principles. Again, let us do it. So, we're given ux equals lambda 1 times x, uy equals lambda 2 times y, and lambda 1 is not equal to lambda 2. Now, what do we need to look at? X dot y. We already know that u does not change the length, so x dot y is the same as ux dot uy. But ux dot uy is lambda 1 x dot lambda 2y. Now, this is the same as lambda 1 bar times lambda 2 times x dot y. So, comparing x dot y on both sides, I get lambda 1 bar times lambda 2 minus 1 times x dot y equals 0. Now, this would imply x dot y equals 0 if we show that lambda 1 bar times lambda 2 is not equal to 1. So we will do that by contradiction. Suppose lambda 1 bar times lambda 2 equals 1. Then we get an easy contradiction, because pre-multiplying both sides by lambda 1 gives lambda 1 times lambda 1 bar times lambda 2 equals lambda 1. Now, using the fact that the absolute value of lambda 1 equals 1 from the earlier property, meaning lambda 1 times lambda 1 bar equals 1, we get lambda 2 equals lambda 1, which is a contradiction. Let me call this equation star. So lambda 1 bar times lambda 2 is not equal to 1, implying x dot y equals 0 from equation star. Now, why are we looking at unitary matrices in the context of Hermitian matrices? I will give a preview before ending this lecture. Coming next, for a Hermitian matrix A, we can find a unitary matrix U such that it equals U times lambda times U star, where lambda is a diagonal matrix with the eigenvalues of A. This is the reason I introduced unitary matrices. We will look at why this decomposition holds. This is the classic spectral theorem, in some form, for Hermitian matrices. If you specialize this to real symmetric matrices, then you get the well-known spectral theorem. For the real case, what we have is for a real symmetric matrix A, we can find an orthogonal matrix Q, meaning Q transpose Q is identity, such that A equals Q times lambda times Q transpose. This is one way of stating the spectral theorem. There are multiple ways of stating this is one way. So we will be proving this theorem in sufficient generality for Hermitian matrices, and the real symmetric case follows as an easy corollary. Before I wrap up this lecture, I would like to summarize the contents of what we saw. Firstly, we defined what a unitary matrix is. This matrix will be used for diagonalizing a Hermitian matrix, which is coming next. Now we saw a few important properties. The intuition is that a unitary matrix, when applied to a vector, does not change the length of the vector. That is one thing we showed using the definition of a unitary matrix. The second thing we showed about the unitary matrix is that the eigenvalues of a unitary matrix have absolute value equal to 1, which is like saying they all lie exactly on the unit circle in terms of magnitude. And the last thing is a claim that we had also shown earlier for Hermitian matrices: if two eigenvalues are distinct, then the corresponding eigenvectors, even for a unitary matrix, are orthogonal. Coming next, we will use unitary matrices to diagonalize a Hermitian matrix. That is in the forthcoming lectures.
Welcome to Lecture 4 in Week 5 of the Linear Algebra segment of Machine Learning Foundations. We will start the discussion of a very important topic in this lecture, which is diagonalization of Hermitian matrices. We will define what it means to say a matrix is unitarily diagonalizable, and then show that a Hermitian matrix is unitarily diagonalizable. The approach for the proof is to show that any matrix, not necessarily Hermitian, any n-by-n complex matrix, can be upper triangularized. We will define this concretely during the lecture, and we use this fact that any matrix is upper triangularizable to show that a Hermitian matrix is diagonalizable. So that is the approach we are going to adopt to show diagonalizability of Hermitian matrices. Just a quick recap. What is a star? A star is just the conjugate transpose. A matrix is Hermitian if a star equals a. A matrix U is unitary if U star U equals identity and U square. A matrix is unitarily diagonalizable if there exists a unitary matrix U such that it equals U times lambda times U star, where lambda is a diagonal matrix. Now, what we want to show is that a Hermitian matrix is unitarily diagonalizable. So the approach is, first, we show that any n-by-n matrix is similar to an upper triangular matrix. So we are not talking about Hermitian matrices here, this is a more general claim. That is, that equals U times T times U star, where T is an upper triangular matrix and U is unitary. Second, using this first result, we show that a Hermitian matrix is unitarily diagonalizable. So that is the approach. So we will prove a more general theorem, which shows that I can take any n-by-n matrix and find a unitary matrix such that I can transform this matrix into an upper triangular matrix. This is like saying that both and T have the same eigenvalues. This more general theorem is called Schur's theorem. This shows that any n-by-n matrix is similar to an upper triangular matrix T. That is, there exists a unitary matrix U such that it equals U times T times U star. Now, we will prove this for a simple case of a 3x3 matrix, but the ideas are so general in this case that it is fairly straightforward to extend this to the more general case. Proof for n equals 3. What is coming next is we will prove this first, and then do an example where we go through the procedure adopted in the proof to arrive at this triangular matrix. Later we will show that Hermitian matrices are unitarily diagonalizable. Given Schur's theorem, it is fairly straightforward to show that a Hermitian matrix is unitarily diagonalizable. You just have to apply Schur's theorem to it, and then use the fact that a star equals it to conclude the main claim of diagonalizability. Whereas showing that any matrix is similar to an upper triangular matrix, which is Schur's theorem, requires a lot more work. So let us understand how the proof proceeds. This proof is important because it also gives a procedure for finding an upper triangular matrix for any given matrix. That is, for any given matrix it gives a procedure or an algorithm to follow so that I get a triangular matrix T such that and T are similar. So let us begin the proof. Let P of lambda be the characteristic polynomial of A. What are the roots of this equation? They are the eigenvalues. Let lambda 1 be a root, just pick one of the roots of P of lambda. Let Z1 be the corresponding eigenvector. Now I can always take a vector and extend it to a basis. So what you do is extend Z1 to a basis, and I can also make it orthonormal using the Gram-Schmidt procedure. You are familiar with this from an earlier course in this degree program. So let us make it orthonormal. For simplicity, let us assume Z1 was picked such that it already has unit length. So let Z1 U V be the orthonormal basis. In particular, Z1 star U equals 0, Z1 star V equals 0, and so on. If I pick any two vectors from this basis, they are orthogonal, and the length of each vector is 1. Now, let me start with a candidate unitary matrix. I will put Z1, U, and V as columns, and call this U1. Now, what happens when I apply it to this? What is a times U1? A times U1 is applied to Z1 UV, which equals a Z1 IU a V. What is a Z1? Z1 is an eigenvector corresponding to lambda 1, so Z1 equals lambda 1 times Z1. That is what we have. Now consider this product U1 star U1. What is U1 star? I have to transpose and then take the conjugate. So the transpose turns Z1 into a row, along with U and V, and I take the conjugate. Multiplying this by a u1 from above, I get lambda 1 z1 a u a v in the resulting product. Now I want to claim that this becomes lambda 1 followed by zeros in the rest of that first column with some other entries elsewhere in the matrix that are not necessarily 0. Why is this true? For this you have to look at this product as z1 bar transpose times lambda 1 z1. This equals lambda 1 times z1 bar transpose z1, but z1 has unit length, so this equals lambda 1. That is the first bit. The second bit is u bar transpose z1 equals 0 and v bar transpose z1 equals 0. This just means that in the very first column, the first entry becomes lambda 1 and the remaining two entries become 0. So we end up with, in general, an n-1 by n-1 submatrix, though in this particular 3 by 3 case it is a 2 by 2 submatrix. You could have started with an n by n matrix and reduced down to an n-1 by n-1 submatrix. We are just doing it here for the 3 by 3 case. So what we have is u1 star u1 equals lambda 1 in the top left corner, zeros below it in that column, some entries across the top row, and a smaller matrix, call it B, in the remaining block. Now repeat the procedure with B. Just take this smaller matrix B, find an eigenvalue lambda 2 of B and a unitary matrix, say P, such that instead of u1 star u1 we now have P star BP equal to lambda 2 in the corner, some number next to it, and then, since we are now down to a 1 by 1 matrix, just some lambda 3 with a star denoting any number, and a 0 below it. We followed the same procedure. Recall, in the earlier procedure, when I computed u1 star u1, I got the eigenvalue in the first entry of the first column and zeros in the rest of that column. Similarly, I do the same for B. Following the identical procedure, I get an eigenvalue lambda 2, extend that eigenvector to a basis, and do the exact same steps, putting basis vectors into a matrix and calling it P. So when I repeat this procedure, I get P star BP equals the same triangular form. Now, what I'm going to do is construct another matrix, U2, which looks like this: a 1 in the top left corner, zeros around it, and P placed in the remaining block. So this 2 by 2 matrix P sits inside the large U2. Now what is U2 star? U2 star has a 1 in the top left, zeros around it, and P star in the remaining block. Now what is U2 star times U2? You can check this directly. Since P is a unitary matrix, P star P equals the identity matrix, so U2 star U2 also equals the identity matrix. Now we are nearly done with the claim. What we have to show now is this: consider the product where I take U2 star, U1 star, multiply with a, and then U1, U2. Look at this product. We already know that u1 star u1 has this particular triangularish form from the first step, and u2 star has the form of the 1, zeros, and P star in the block. So multiplying u1 star u1 gives lambda 1, some numbers across the top, a 0 below, and the matrix B in the remaining block. Then u2 contributes the 1, zeros, and P in its block. Now this product becomes lambda 1, some numbers across the top, a 0 below, and then in the remaining block P star BP. But we already showed that P star BP has lambda 2 and lambda 3 along its diagonal, so it is upper triangular. So what we have done, incrementally, is arrive at a matrix that is fully upper triangular with lambda 1, lambda 2, and lambda 3 along the diagonal and some other entries above it. So what we have concluded is that u2 star u1 star u1 u2 is an upper triangular matrix. Are we done? There's one final detail to work out. What is the final u? Set u equal to u1 times u2. Then u star equals u2 star times u1 star, which equals u2 inverse times u1 inverse, which equals u1 times u2 inverse, which equals u inverse. So u is unitary, and u star u equals u2 star u1 star u1 u2, which is upper triangular. Or equals u times t times u star. That is the end of the proof. So that is Schur's theorem. The proof is fairly general. As a remark, the proof can easily be extended to a general n greater than 3. It is very, very straightforward. I think it can be an easy homework exercise. What we will look at next is an example. Let us look at an example where this procedure comes into action. Let us take the matrix with rows 5, 8, 16, 5, 0, 9 and -3, -5, -10. The problem is to upper triangularize it, not diagonalize it, just upper triangularize it. So let us start with the characteristic polynomial. This is just a rehash of the proof, going through the same steps. What is the characteristic polynomial? You can pause and work this out on your own. I'm not going to give all the details since it is fairly straightforward. Just check that this is the correct characteristic polynomial. It is clear that you have a repeated eigenvalue, so it may not be diagonalizable. The eigenvalues are lambda 1 equals 1 and lambda 2 equals -3 repeated. The eigenvector, let us call it z1, you can check, comes out to be -2, -1, 1 by solving a minus the identity times x equals 0. Now recalling the procedure in the proof, I take Z1 and add the standard basis vectors E1 and E2. So the set is -2, -1, 1 together with 1, 0, 0, and 0, 1, 0. This is a basis for R3. Now what we do is apply the Gram-Schmidt procedure to obtain an orthonormal basis. Recalling the proof, my first matrix U1 turns out to have, for the very first vector, just the normalized version -2 over the square root of 6, -1 over the square root of 6, 1 over the square root of 6. The other columns require more work, you have to do the Gram-Schmidt process yourself. I will just give the answer 0, 1 over the square root of 2, 1 over the square root of 2 for one of the remaining columns. It is easy to check whether this is a unitary matrix, just take the dot product of the columns and verify. Now, what is U1 star U1? There are no complex numbers here, so it is just U1 transpose U1. This turns out to be, by construction, 1, 0, 0 in the first column, with some other numbers appearing elsewhere. Those numbers turn out to be -8 times the square root of 2, and -12 times the square root of 3. The important bit is that you get a smaller matrix inside. Let us focus on the smaller matrix next, and call it B. The next step is to find an eigenvalue of B. Here, you get lambda 2 equals -3 with the corresponding eigenvector. Now, it is very easy to extend this to an orthonormal basis. Take the standard basis vector E2, and to make an orthonormal basis, take E1, which is like taking 0, 1, and adding 1, 0. This extends to a basis of R2. From this, I make the unitary matrix, call it P, which is just made up of these basis vectors. And P star BP equals P transpose BP, and this turns out to be a triangular matrix. So we have P. How do we make up P2? We put a 1 in the corner, zeros around it, and P, which is 0, 1, 1, 0, in the remaining block. You can recognize this as a permutation matrix if you are familiar with it, but that detail is not something you need to worry about further. The important bit now is to look at U2 star U1 star U1 U2, which is U2 transpose, U1 transpose A, U1 U2. I will leave this as homework. It's a simple matrix multiplication. It turns out to be a matrix with 12 times the square root of 3, 0, 0 in the top row, and then P star BP filling in the rest. You would not have to multiply anything new, all the ingredients are already there. U1 star U1 is something you already know, and you just patch in P star BP. This gives the upper triangular matrix. So, setting U equal to U1 times U2, we have U star U equal to an upper triangular matrix. That is the upper triangularization of A. We went through this procedure for a matrix that, if you observe, is real but not symmetric. So we did not get a diagonal matrix from this. We got an upper triangular matrix. In particular, this matrix had a repeated eigenvalue, so if we had had 3 distinct eigenvalues, we would have gotten a diagonal matrix. But in this particular case, since it had a repeated eigenvalue, we did not get enough eigenvectors to diagonalize it fully. Still, we were able to upper triangularize it. So we will end this lecture with a recap of what we learned today. We understood what it means to say a matrix is unitarily diagonalizable. The next thing was a proof, followed by an example of the fact that any n by n complex matrix is upper triangularizable. This is the well-known Schur's theorem. We actually proved this for the 3-dimensional case, but the proof is so general that it can easily be extended to any higher dimension. The proof also gave us a procedure for upper triangularizing a matrix, and we followed the steps adopted in the proof to arrive at the upper triangularized form of a 3x3 complex matrix that we constructed. Coming next, we are going to use Schur's theorem to show that any Hermitian matrix is unitarily diagonalizable. That is coming in the next lecture.
Welcome to Lecture 5 in Week 5 of Machine Learning Foundations. We're continuing the discussion on the linear algebra side of things. In this particular lecture, we will be able to prove the most important theorem that we wanted to get to, which is the spectral theorem. In essence, this states that a Hermitian matrix is unitarily diagonalizable. Do note that this is not an if and only a statement. So if a matrix is unitarily diagonalizable, that does not imply that the matrix is necessarily Hermitian. All we are saying is that if a matrix is Hermitian, then it is unitarily diagonalizable. Now, an important corollary of this fact in the context of real vector spaces is that a real symmetric matrix is orthogonally diagonalizable. That is the version of the spectral theorem for real symmetric matrices. We will prove the spectral theorem for complex matrices for Hermitian matrices by using what we proved in the previous lecture, which is Schur's theorem, stating that every matrix is upper triangularizable. We use this fact to show that a Hermitian matrix is unitarily diagonalizable, and then we will go through a few examples after that. Now, the main theorem, the so-called spectral theorem, in its most general case, says that any Hermitian matrix is unitarily diagonalizable. That is, there exists a unitary matrix U such that a Hermitian matrix satisfies U star U as a diagonal matrix with real numbers. The proof is very simple given Schur's theorem. From Schur's theorem, what we have is that U star U is an upper triangular matrix, call it T. Now, let us look at T star. This is U star star U, but this is the same as U star U because it equals a star since it is a Hermitian matrix. But U star U is just T by construction. Now T is an upper triangular matrix. So what is T star? T star would be a low triangular matrix. So if you have T with entries above the diagonal and zeros below, then when you take its conjugate transpose, T star, you move all the entries that were above the diagonal to below the diagonal. Now T equals T star can only happen if T is diagonal. So we have T as a diagonal matrix. So U star U equals T, where T is a diagonal matrix. This is not all. We also claim that the diagonal entries are real. So let us also show that T equals T star implies if you consider just the diagonal entries T sub II equals T star sub II. This is the same as saying T sub II equals the conjugate of T sub II, which implies T sub II is a real number. So the final claim is U star U equals T, with T denoting a diagonal matrix with real entries. That is the end of the proof. So let us look at an example. It is easy to check that a star equals a. What is the characteristic polynomial of a? P of lambda equals lambda minus 1 times lambda minus 4. So the eigenvalues are lambda 1 equals 1 and lambda 2 equals 4. It is a very simple matrix, so I'm just going to write down the eigenvectors directly. Let us call the first one z1 equal to minus 1 plus I, 1 corresponding to lambda 1. And z2 equals 1, 1 minus I. It is easy to check that z1 transpose z2 equals 0. But we need a unitary matrix, so we need to do a little more work. So we normalize z1 and z2 to obtain u1 and u2. u1 is just the normalized version, so it is minus 1 plus I divided by the square root of 3, 1 divided by the square root of 3. u2 equals 1 minus I divided by the square root of 6, 2 divided by the square root of 6. And then let U equal the matrix with columns u1 and u2. Then what is U star U? U star U can be verified to be a diagonal matrix. A very important corollary to the result above is the following. The real-world counterpart of a Hermitian matrix is a real symmetric matrix. And in the real world, instead of the unitary concept in a complex vector space, we have orthogonal. So a real symmetric matrix is orthogonally diagonalizable. That is, there exists a matrix Q such that, instead of U star U, I take Q transpose a Q and I get a diagonal matrix where Q transpose Q is identity, because Q is an orthogonal matrix, and the result is a diagonal matrix with real entries. This is the spectral theorem. And the proof is fairly straightforward. I will just give it to you. From the claim for Hermitian matrices, we have U star U equals U inverse U equals D, a diagonal matrix. And the columns of this matrix U are the eigenvectors of and that is given. Now, it is clear that is real symmetric, which is the same as saying it is Hermitian, and this implies the eigenvalues of are real. So if I look at a minus lambda times the identity times x equals 0, solving this leads to a real vector x. And this implies U is a real matrix, so U star equals U bar transpose equals U transpose equals U inverse. That is all there is to it. Hence, we have U transpose U equals a diagonal matrix with U transpose U equal to identity. I will end this topic with one final remark, which is the following. We have shown that if a matrix is Hermitian, it implies that it is unitarily diagonalizable, but this does not mean that the only unitarily diagonalizable matrices are Hermitian matrices. In particular, the converse is not true. So, to see this, consider a simple matrix such as the one with rows 0, minus 1, and 1, 0. It is easy to see that a star is simply not equal to a. But you can still always find enough eigenvectors. The eigenvalues are lambda 1 equals I, you can check this, and lambda 2 equals minus I. This already implies distinct eigenvalues, which implies is diagonalizable, and the corresponding eigenvectors are z1 equals 1, minus I, and z2 equals 1, I. We can normalize these. Normalizing just two vectors is easy, so u1 is just the vector divided by its length, so 1 divided by the square root of 2, minus I divided by the square root of 2. And u2 is 1 divided by the square root of 2, I divided by the square root of 2. All you have to do is form the matrix U from u1 and u2, and you can check that U star U is I, 0, 0, minus I. A recap of what happened in today's lecture. What did we learn today? The first thing we understood today was that we could state and prove the following claim: a Hermitian matrix is unitarily diagonalizable. Now, this result, in the context of real vector spaces, states that a real symmetric matrix is orthogonally diagonalizable, which is a very important result, well known as the spectral theorem. And then we did a few examples to verify this fact, both for a complex matrix and for a real symmetric matrix. In the complex case, we took a Hermitian matrix and we could unitarily diagonalize it. And lastly, we exhibited a matrix which is unitarily diagonalizable but which is not Hermitian. So please do understand this claim well. If a matrix is Hermitian, it is unitarily diagonalizable, but the converse is not true. There are matrices which are not Hermitian but are still unitarily diagonalizable.
Hello everyone. In the previous two videos, we discussed the application of singular value decomposition in image compression at how it approximates an original image using different ranks, followed by a discussion of the geometric interpretation of singular value decomposition, especially in Euclidean two-dimensional space, at how it transforms a geometrical shape. I hope those were good motivating examples. So in this video, there are some questions to think about and a few questions to solve. It is a kind of computational session along with some interesting conceptual questions. Here is the setup. In linear algebra, when machine learning, when deep learning, or generally in scientific fields, we often deal with n-dimensional space, not just 2 or 3. We usually go beyond 3, such as 100, 1,000, or even 1,000,000 dimensions. In such a case, it is very difficult to visualize what is going on in the millionth dimension. So what do pioneers in this field actually do in such a case? When they see a vector or a matrix of dimension n greater than 3, how are they able to visualize it? Let us see how they deal with it. So to deal with hyperplanes that are greater than 3-dimensional, say in a 14-dimensional space, what they do is simply picture a 3-dimensional space and say 14 to themselves. It is a quote, I'm not entirely sure of its exact wording, attributed to none other than Jeff Hinton. I do not know whether you are aware of him. He is a pioneer in deep learning and machine learning in general, and a pioneer in neural network architectures. You can do a quick search and learn a lot about him. So that is the case. We usually try to understand the concept in R2 and R3, and then, if you want to know how something behaves in R100, you just say 100 to yourself. In line with this, the week 5 content is all about complex matrices. So the obvious question that comes to mind is, can we visualize a complex vector? Think about it. Is it possible to visualize a complex vector the way we do for real vectors? In the real case, suppose you are given the vector x equal to 1, 1. You can take two real axes, orthogonal to each other, and simply plot the vector from the origin to the given point. That is what we do in a real vector space. But what about a complex vector space? Think about it. Pause this video and think about it. After thinking harder, is it really possible to visualize a complex vector? Let us start with visualizing a single complex number. Say, for example, if I have 1 plus I, which is a complex number, an element of C. We do visualize a single complex number using two real axes, one we call the real part and the other, orthogonal one, we call the imaginary part. Now, if I have another complex number, an element from C2, the question is if I have a vector x that comes from C2. For example, if I add one more vector here, say 1 minus I, now I have two elements from C. How can I plot it? Think about it firsthand. Obviously, it is not possible to visualize a vector from C2 or anything larger than C2. The reason is that if we want to plot the other element, we need two more axes. So for a single complex number, we need two real axes, one real and one imaginary. So if we want to plot a complex vector from C2, we need 4 axes, which means we need 4 dimensions. We cannot do that even in 3 dimensions. So to visualize a vector from C anything more than C2, we need 4 dimensions for C2. In general, we can say C2 is equivalent to R4 and C3 is equivalent to R6. For every complex number, we need 2 axes, so we have to keep adding 2 axes. So it is not possible to visualize a complex vector, but we do not really care about that because we have an algebraic way of manipulating the vectors. That is one skill we should have. Apart from visualizing things, we should be comfortable algebraically or logically manipulating all of this. So that is about complex vectors, but what about complex matrices? So far, even in the application of singular value decomposition, we considered a matrix from real space. All the elements in the matrix were real numbers. But now, if we think about complex matrices, some or all of the elements in the matrix are going to be complex numbers in general. So the immediate question that naturally comes to mind is, do we really find applications of complex matrices? Is that just some other mathematical construct that comes out of axioms, some kind of pure math for those who do not care about real-world applications? This is an obvious question we need to answer. I can give you an answer. Take a look at this matrix.
This is actually a complex matrix which contains, as you can see, some complex numbers. Of course, you can ask whether it is symmetric or Hermitian or a Hermitian symmetric matrix, and you can talk about all sorts of properties or types of complex matrices. But the question is, are the elements in this matrix random? Did I just insert those elements so that it would look like a complex matrix, or does it come from some real concept? This matrix, which is a 4x4 matrix, comes from a transform, a mathematical transform which we call the discrete Fourier transform. The Fourier transform is one of the core transforms applied in many domains. You may not need to be aware of the details, by the way. But just to answer your question about whether complex matrices find any real-world applications, I have to tell you that this is one of the important, and there are many complex matrices, but this one is extremely important. So you should be very happy now because you are not studying something abstract, something purely mathematical. You are studying something that is applied in the real world in many applications. To give you some examples, there are countless applications of the discrete Fourier transform, especially in signal processing domains like communication devices, wireless communication, and your entire mobile phone. The antennas in your mobile phone, all the signal communication, is actually developed using the discrete Fourier transform. They are somehow applying the discrete Fourier transform in your mobile devices. You can find such components in speech processing and noise cancellation as well. I could list out a lot more, but this is really a subject of its own. If you want to study discrete Fourier transforms and their applications, you would need another course on signal processing and related topics. We need not go into that here, but I just wanted to tell you that yes, there are applications of complex matrices in the real world. You can just take that for granted, but trust me on that. Now, let us set all that aside and solve some problems from the Week 5 content. The first important problem is computing the dot product with the inner product between two complex vectors. Here are two vectors, x and y. You can read the elements in x and y. We have to verify, for the specific example, whether the commutative property is applicable. Are these two vectors, when we compute the dot product, going to be commutative? Which means I have to compute the inner product between x and y, and then commute it, computing y dot x, and see whether both of them give the same result. By doing that, we can verify whether it is commutative or not. Of course, we can prove it in general, but we are just taking this example to check, and if the equality does not hold for this example, then it is not true in general. So we have essentially come up with a counterexample. So what should we do? Recall the formula. If you want to compute the inner product of two complex vectors, first you take the conjugate of the x vector, and then you transpose it. Taking the conjugate is very important. Then you multiply the elements of these two vectors element-wise. It goes like this. First, we take this element and conjugate it. So 3 minus 2i becomes 3 plus 2i. Then I take the first element from y as it is. We are not doing any conjugation there. We simply multiply the two complex numbers. Similarly, I take the second element, conjugate it, then take the second element from y and multiply it. You keep doing that and finally you sum everything up. It is very simple. You just multiply two complex numbers. If you multiply these two complex numbers, you get a complex number as the answer, which is minus 14 plus 8i. Similarly, you take the second element from x conjugated, which is minus 2 minus I, and then take the second element from y and multiply them together, and you get another complex number. You take the third element, conjugate it, and multiply by the third element from y, and you get another number. So what you have to do after multiplying all these elements is sum up the results. We can visualize this as feeding everything into a summer, adding up all the elements to get the answer. So, if you multiply these two complex vectors in the order x followed by y, you get the answer minus 19 plus 13i. Now, the question is, will it be true if I interchange the order of the vectors? Instead of x dot y, what happens with y dot x? Let us take a look. By definition, y dot x, the inner product between y and x, is y conjugate transpose, which is y Hermitian multiplied by x. Let us do that. Again, you take the vector from y, conjugate its elements, and multiply by the corresponding elements from x. The first element from y is minus 2 plus 4i. If you conjugate it, this becomes minus 2 minus 4i. Then you simply multiply this with the first element from x, which is 3 minus 2i, and we do not take any conjugate for the elements in x because we only conjugate the elements in y. If you keep repeating this, taking the second element from both vectors, and then the third element, you get several numbers, and then you sum them up. This gives minus 19 minus 13i. So compare the results of the previous one, x dot y, with this one, y dot x. What is the change? The real part remains the same, but the imaginary part is, in a sense, the conjugate. So, in general, y dot x is not equal to x dot y. Here, the answer you could interpret as whatever answer we obtained for x dot y, which was minus 19 plus 13i, y dot x is simply the conjugate of that, which is minus 19 minus 13i. So now, with the help of this example, we know that x dot y is not equal to y dot x. In other words, we say it is not commutative in general. You can think of some examples for under what conditions or for what types of vectors this x dot y becomes equal to y dot x. You can think about such examples yourself, I leave that to you. Now, let us move on to another proof, which is a simple one. There are many properties of this inner product space. We've just seen through a specific example that x dot y is equal to the conjugate of y dot x. We considered a specific example and noticed that it holds true for that example because x dot y equals the conjugate of y dot x. But is it always true for all examples? For that, we have to prove it. The proof goes very simply. It is not a tedious one, so you can just pay attention. You can write y dot x and then take the whole conjugate as follows. Remember, we replace the dot product with y conjugate transpose times x. Then you can expand this. We simply take the conjugate of all the elements in y, which becomes y1 conjugate, y2 conjugate, and yn conjugate, and multiply by the respective elements from x, x1, x2, and so on up to xn. Then we take the whole conjugate. There should be an overall bar on top, but using the property that the conjugate of a product, a times b, equals the conjugate of a times the conjugate of b, we can rewrite this. Applying this, it becomes something like y1 conjugate of conjugate times x1 conjugate. But the conjugate of y1 is simply y1. So we simply shifted the conjugate from y to x. You can rewrite this by interchanging the elements in the product, and now you can write this as x dot y. So now we have proven that x dot y equals the conjugate of y dot x. We considered the right-hand side and showed that it equals the left-hand side. You could also do it the other way around, but this direction is straightforward. So the proof is simple. Let us move on to the next question. Usually, in a real inner product space, where we are given two vectors in real vector space, apart from computing the inner product, this inner product also helps us find the angle between two vectors. If I have vector x and vector y in, say, R2, then computing the inner product gives me the projection of x onto y and also allows us to obtain the angle between x and y. In the same way, can we use the inner product in the complex space to compute angles in the complex space, angles between two complex vectors? There is some ambiguity here that we have to acknowledge. The answer is not always. The reason is that in order to compute the angle between two vectors, we use the formula involving x dot y divided by the length of x times the length of y. If x comes from a real vector space, x dot y is going to be a real number, and the lengths of x and y are also real, so we can compute the cosine of the angle because the result is a real number, and we can make sense of it. But in the case of a complex vector space, x dot y is not always going to be a real number. For some vectors it might turn out to be real, but for other vectors it turns out to be complex. Defining a cosine angle in the setting might give rise to some ambiguity or an inconsistent definition of angle. So some authors prefer to take just the real part of the result and compute the angle from that. But there are differing opinions about this, so you can read about the summary. You can refer to a paper if you are interested. There is a link that I will post along with the slide in the portal, so you can download and use it. Having said that, we are now moving on to another problem. So far, we have been able to compute eigenvectors for real matrices. Given a real matrix, you know how to find the eigenvalues and also how to compute the eigenvectors. Here is an example where the matrix is actually complex, and the question is, can we find the eigenvector for this complex matrix? Of course we can. There's no change in the procedure. You follow the same steps, you compute the eigenvalues, and for a given eigenvalue, you compute the eigenvectors just as you would for a real matrix. There are no differences at all. In this case, you are given the eigenvalue, and we have to compute the eigenvector. The n here denotes the null space. You substitute lambda and subtract accordingly, and you end up with this matrix, which I have taken from the lecture. I'm just going to show you how to obtain the eigenvector for this matrix for the given eigenvalue. So what do? First, we have to reduce the matrix. If you notice, I have minus 6 here and 3 plus 3i here, and I want to make this entry 0. So what should I do? I simply multiply the first row by a particular complex number. If the matrix were real, you would use a real scalar. Now it is a complex number. You can figure this out. It turns out to be 1/2 times 1 plus i, because the entry is 3 plus 3i, and I want it to become minus 3i times something, so we multiply this complex number by row 1, and then add the rows together. You get a matrix with entries like minus 6, 3, and so on. So now I can simply find the eigenvector by finding x1 and x2 that belong to the null space of a minus lambda times the identity. Since all the elements in the second row are 0, we get a simple equation minus x times x1 plus 3 minus 3a times x2 equals 0. Now x1 and x2 are free variables, so we can assign a fixed value to one of them. We can write this the final equation as 2 times x1 equals 1 minus I times x2. We put a value for x1, say x1 equals 1, and then find x2 accordingly. So x2 turns out to be, since x1 equals 1, 1 minus 1i, which is what you see here, 1 minus 1i. Instead of writing it a different way, I'm using this notation that is just a formatting choice. You can ignore it if you want. So this is an eigenvector, but we can rewrite it using a complex quantity in the denominator to enhance it. If I rewrite x2 this way, you get x equal to 1 and 1 plus 1i. So the corresponding eigenvector for the eigenvalue lambda equal to 8 is 1 and 1 plus 1i. Of course, any scalar multiple of this vector, 1, 1 plus I, is also an eigenvector of the matrix for the eigenvalue lambda equal to 8. And here is a question for you to think about: should the scalar multiple be a real number, or could it be a complex number? Is any complex multiple of this x also an eigenvector, or only real multiples of x? Think about it. Similarly, you can find the other eigenvector for the matrix A, following the same procedure. The reason I am solving this in this tutorial problem is that if you want to do eigendecomposition for this matrix A, you have to find the eigenvectors first. Since it is a complex eigenvector, I think this example will help you find complex eigenvectors for any given matrix. The procedure is going to be the same. So the next problem is about the unitary matrix. Recall that we say a given matrix U is unitary if U times U transpose, where U times U Hermitian gives an identity matrix. In this case, we're given U, and we have to check whether it is unitary. For that, we need U transpose. Since all the entries are real numbers, we are just writing this as U transpose. If we simply transpose the matrix, we get a certain matrix. Then we multiply U and its transpose, like we do for regular numbers. It does not matter that the elements of the matrix are functions rather than numbers. The way we multiply matrices is the same. So we do the matrix multiplication, and once you do that, you get a resulting matrix. It is very simple because cosine squared plus sine squared appears in the computation. You can see that after multiplying, though the matrix looks big, it is not actually complicated. We have a cosine t sin t term here, and the sin t cosine t term here, and these cancel to become 0. Similarly, we have a sin t cosine t term here and a cosine t sin t term here, and subtracting these gives 0. This term you should recall is cosine squared theta plus sine squared theta, which equals 1, and this other term is also going to equal 1. Remember, t can take any value from 0 to 2 pi, but it does not matter what value t takes it. We simply substitute t and show that the result is, in fact, a unitary matrix. All the elements give us an identity matrix as the result, 1 0 0 1. Of course, we could change the sign of something and still get a similar result, and it would still be a unitary matrix. You can prove this for any given matrix. You take U and U Hermitian or U transpose and see whether the product is an identity matrix. If it turns out to be an identity matrix, then it is a unitary matrix, and our unitary matrix is also an orthogonal matrix in this case, since it is real. So we can say it is an orthogonal matrix as well. Now we have seen that unitary matrices have some interesting properties, especially that they preserve the length of the vector being multiplied. Here is an applet that demonstrates this. In this example, take a look at the elements of the matrix, which are the functions cosine t and sine t, and as I mentioned, t can take any value from 0 to 2 pi, and for all values of t it is going to be unitary, not just for t equal to 0 or t equal to pi, but for all values of t it is going to be a unitary matrix. I'm going to substitute various values of t into this matrix, and multiply that matrix with a vector x shown here. In the applet, the vector x is of course in R2. The input vector to this matrix is this: the vector is 1, 0, so x is 1 and y is 0. If I apply the matrix, we are doing a matrix transformation, multiplying a matrix by a vector, so we transform the vector. Since this is an orthogonal matrix, it is going to transform the vector in some way. Let me substitute various values of t and generate different matrices and apply each one to this vector x to see what happens. Now t varies from 0 all the way up to 2 pi. When I vary t from 0 to 0.16, you can see that it transforms the vector x into a new location, denoted by this red vector, y. If you look carefully, the length of the vector has not changed. It is neither stretched nor shrunk, it remains the same. So what changes? It just changes direction, meaning it is rotated. Let me change the value of t further. For each value of t, we get a new matrix, but all of them are going to be unitary. Let's see what happens. I am changing the value of t now to about 3.14, which is roughly pi, so now we are halfway through. All these different matrices acting on X transform X while preserving its length but just changing its direction. If I continue this all the way up to about 6.28, which is roughly 2 pi, you can see that the vector has made one full anticlockwise rotation. So you can see that it preserves the length of the vector throughout. We have now visually demonstrated that yes, it preserves the length of the vector. What happens if we apply an ununitary matrix? Say, for example, I'm calling this an ununitary case. I do not know whether that's a standard terminology, but let us say I apply some other matrix. Let us see whether it preserves the length of the vector x being transformed. So, instead of the unitary matrix, I'm going to consider a matrix composed of a cosine term here and a tangent term there. Of course, you can show that if you multiply this matrix by its transpose, you do not get an identity matrix, so we can say it is not a unitary matrix. Now, does it preserve the length of the vector x when applied? For some values of t, maybe, but in general, it does not seem to preserve the length of the vector x for all values of t. So we can say that for some values of t, it might happen to be unitary in effect, but for other values of t, it is not. So the matrix with cosine t minus tangent t, cosine t is not unitary in general, but the previous matrix with cosine t minus sine t, and cosine t is unitary in general for all values of t. And you can see that for an ununitary matrix transformation, the length of the vector is not preserved when it gets transformed. So now I hope you get some idea about unitary matrices and what we mean by length preservation and all these related ideas. Even if you do not fully get it now, that is fine, you can work through a few more examples and figure it out on your own. There are also a few more concepts about solving for the singular value decomposition, but since you already know how to compute the eigenvectors of a matrix, doing the same for singular value decomposition will not be too much more difficult. I did not come up with examples for that here, but we will solve such problems in a Solve with Instructor session. You also have a few problems in the activity and practice questions, so please work through them, and if you have any doubts, let us discuss them in the open session. Thanks for watching this tutorial, and if you have any doubts, please note them down. Hoping to see you all in the live session. Bye bye.